Hello students, and welcome to section 1.5 and 1.6 combined. In section 1-5 we're going to be taking a look at solving inequalities. To start with, one-step inequalities. So the following properties can be used to solve inequalities. For any real numbers a, b, and c, if a is less than b, then a plus c is less than b plus c, and a minus c is less than b minus c. The idea here is you're adding the same number to both sides in some cases, or you'll be subtracting. The same holds true with greater than, as you can see the inequality carrying over. The multiplication and division properties for inequalities are as such. When you divide both sides by a negative, that's the biggest nuance where, and multiply for that matter, where the inequality flips from less than to greater than. And as you can see here, starting with a is less than b, multiplying both sides by c will flip the inequality from less than to greater than. But also if you divide both sides by c, again c being negative, you'll have to flip the inequality accordingly. The same holds true if a starts to be greater than b. Multiplying both sides by c, it flips to less than, and then dividing, it flips to less than. These properties are true as well for less than or equal to and greater than or equal to. Now I didn't have an opportunity there to discuss the positive numbers, but as it turns out, positive numbers will not affect in the multiplication nor the division aspects in terms of the flipping of the inequality, because as you can see, the inequality does not flip in either case. So example 1. Solve 2x plus 4 is greater than 36. So to solve this, we're going to go ahead and take a look at the balancing, obviously, of both sides. We subtract 4 from both sides, and in doing so you get 36 minus 4, of course, 32. Divide by 2, you get 16. So x is greater than 16. There'll be an open circle at 16 and everything graphed to the right. So parentheses 16 to infinity. Example 2. Solve 17 minus 3w is greater than or equal to 35. So the same principles apply with balancing the equation. As you can see, subtract 17 from both sides. Okay, and it's going to cancel there. And you'll end up with negative 3w is greater than or equal to 18. If you divide both sides by negative 3, you're left with w is less than or equal to negative 6. So you'll have a bracket at negative 6. And then as you see off to the left, you see negative infinity. Because as it turns out, this inequality, w is less than or equal to negative 6. You have a closed circle at negative 6 and graph everything to the left. So there you have it with your interval notation as well. There are several problems that follow. I would like you to please try those problems that you see in red, and also the circled question there, number 8. Please give those a try. There are elements of those questions in which you will have some similar balancing, but also you'll have some, in some cases, also dividing by a negative or multiplying both sides of an inequality by a negative. So make sure you flip the inequality in those cases. Next page. We did discuss this in class, so I'm going to just highlight the basics. If you recall, when we looked at this multi-step inequality scenario, I highlighted some of the aspects of the word problem itself with 3/4. After those 3/4 have passed, the Tigers have won 48 out of the 72 games. How many of the remaining games must they win in order to win more than 70% of all their games? 0.7, of course, will be that decimal. If you recall, we set up our inequality as such. So it's 3/4, again 3/4, times the quantity 48 plus x. X again being the number of remaining games the Tigers must win. 3/4 times this quantity will be greater than or equal to, I added the or equal to, so at least 70%. But again, we know that it's out of 72. So we actually can do that math. 0.7 times 72. Multiply both sides by 4/3. And then if you see here, you have 4/3 times this quantity, and this ends up being 67.2. Subtract 48. If you recall, we ended up with this. Now this number is technically not the number of games that they have to win, so we round up in order for us to get that percentage to just surpass 70%, so 20 or more games. I'm going to scroll down for you, and I would like you to please take a look at number 1 and number 3 on your own. These two are similar scenarios to just basic solving inequality problems that we've already kind of seen so far. Please take a look, and you'll find, again, in the simple balancing, multiplying both sides by 3, subtracting 4, dividing by 2. And in this particular question, multiplying both sides by 5, subtracting 2h, and then dividing by 13, you'll get this inequality. But try that out. Write out the steps, and please also graph as you see, and hopefully it looks like what your graph shows is what you see here. Okay, number 4. Jim makes $5.75 an hour. Each week, 26% of his total pay is deducted for taxes. How many hours does Jim have to work if he wants his take-home pay to be at least $110 per week? Write and solve an inequality for this situation. So here, this represents the number of dollars times, in this case, the dollars per hour times the number of hours technically. So that will end up being a dollar amount. And then you're going to subtract. Okay, it's deducting, right, 26%, so 0.26 times, or of really, this quantity again that you saw in the beginning, 5.75x. So again, this quantity minus the deduction of 0.26 times the same quantity. Again, he wants it to be, though, at least, so greater than or equal to, $110 per week. If you simplify these two, in other words, if you actually do 5.75 minus 0.26 times 5.75, and then you divide both sides by your coefficient, 110 divided by that quantity should end up being 25.85 hours. And that's a perfectly good final answer for what we're doing here. I'm going to segue into section 1.6, because section 1.6 does detail, as you can see, solving compound and absolute value inequalities. So it segues quite nicely. Compound inequalities. A compound inequality consists of two inequalities joined by the word and or the word or. To solve a compound inequality, you must solve each part separately. So an and statement, an intersection we call it, has this shape to it. Okay, now in most instances we're going to kind of negate this this notation, excuse me. We're not going to need to note it because the word and or, frankly, just combining the inequalities is enough to designate that it is in fact an intersection. This is in some instances something we will use, but it's to help you kind of frame, okay, and statements versus or statements. This union symbol, we call it, the union symbol will be used in context on various problems, which we will see here. But the and statement will kind of take the place, or better yet, when it all is said and done, you should just combine it if in fact it is an and statement. Okay, and you'll see in a little bit here how the union symbol is used on or statements, of course. So example 1, solve -3 less than or equal to 2x plus 5 less than or equal to 19. So I'm going to break down as they do here, and I would have broken this down the same way. If you see the first inequality as this, -3 less than or equal to 2x plus 5, and 2x plus 5 is less than or equal to 19, subtract 5, so -8, divide by 2, so -4, x is greater than or equal to -4. The second inequality, subtract 5, 14, divide by 2, 7, x is less than or equal to 7. So if I combine these two inequalities, and yes, you can, because again, it's an and statement, -4 goes on the left, that's less than or equal to, I'll read it from this perspective because that's probably a little bit easier to identify here, -4 less than or equal to x, which is less than or equal to 7. Put it all together, and there you have it. Closed circle at -4. We've got also a closed circle at 7, and everything graphed in between. Bracket at -4, bracket at 7, and that speaks to your final interval notation. Example 2. Solve 3y minus 2 is greater than or equal to 7, or 2y minus 1 is less than or equal to -9. Graph the solution set on a number line. 3y minus 2 greater than or equal to 7, that's or what? 2y minus 1 less than or equal to -9. That's set up with an or again in between. Add 2, divide by 3, y is greater than or equal to 3, or add 1, negative 8, divide by 2, negative 4. So again, this or that. Putting it all together, a little bit of a different notation again, noting the U symbol or union symbol, right? So y less than or equal to negative 4, that's going to be closed and to the left. So negative infinity to negative 4 with a bracket. And union with, okay, 3, that's going to be closed and graphed to the right. So bracket at 3 off to infinity. Okay, I do want to request that you guys try problems 7 and 8. Okay, problem number 7 is a pretty typical AND statement. Like you see down below, this is kind of how most AND statement graphs are going to unfold anyways, while most OR statements unfold like this. So number 7 is a fairly good question to segue from those examples up top and try out. Number 8 is a little bit more interesting, so let's speak about number 8. So you've got this inequality, 4d minus 1 is greater than negative 9, or 2d plus 5 is less than 11. In this first inequality, we add 1. 1 minus 9 is negative 8, divide by 4, negative 2. Or we get on the other, 2d is less than, subtract, and boom, you get 6. Divide by 2, d is less than 3. So this inequality is going to tell you on the graph at least that it's greater than a negative 2 from the right. And this is going to tell you here's 3, open circle, to the left. So here's the problem. Because most OR statements are going to look like this, these two overlap one another. And by definition, if it's an OR statement, this could be true or that could be true. And if we were to pick a number like, I don't know, pick a number like 0. So 0 is between these two. It's greater than negative 2, but it's also less than 3. Well, what about a number over here, like 4 or 5, and so on? If you pick a number that's greater than 3, it is in fact greater than negative 2, or it is in fact also less than 3. It's technically not less than 3, but the word or allows the number like 4 to actually work. Similarly, negative 4 should also work. For this particular inequality, we know negative 4 is in fact less than 3, but it's not greater than negative 2. Again, the word or means that one or the other is true. And because of the nature of how these are taking shape graphically, all real numbers or negative to positive infinity is how we can write the interval notation for this. Moving on. So this is a nice kind of combination of things. We're going to combine absolute value with inequalities, hence absolute value inequalities. Use the definition of absolute value to rewrite an absolute value inequality as a compound inequality. So if you guys see a less than inequality, that's going to be indicative of an AND statement. Negative b less than a less than b. If you see a greater than inequality with an absolute value, it'll look something like this. This is an OR statement. So a is greater than b, or a is less than negative b. All right, the goal, so to speak. Here's a way to remember it. If you see a greater than or equal to symbol, we know it's going to be an OR. And if you see a less than or equal to symbol, you know it's going to be an AND statement. The absolute value bars are also crucial in this particular type of setup. Example 1, solve the absolute value of x plus 2 greater than 4. We know it's an OR statement by virtue of the inequality, so greater than OR. To solve this, we can set up one inequality as such, x plus 2 is greater than 4, or x plus 2 is less than negative 4. So you flip the inequality and you switch the sign for, in this case, the negative. To solve each, it's pretty straightforward. We'll subtract 2 to get x is greater than 2. Or excuse me, sorry, subtract 2 to get, yes, x is greater than 2. We're good. And then on this guy, we'll subtract 2 to get x is less than negative 6. Again, it's an OR statement. Notice your graph. Open circle at negative 6 to the left. Open circle at 2 to the right. And that right there is your final answer in interval notation. Negative infinity to negative 6 in union with 2 to infinity. Please read through example 2. This is an AND statement by virtue of a less than inequality, so AND. And notice the setup. You can use negative 5, flipped it over to the other side as such. So negative 5 is less than this, which is less than 5. Solve that. There's your inequality. There's your interval notation. And see if your graph makes sense as well. Please finish up those circled questions.